Okay, this is our second video in our linear momentum module, and in this video we're going to get into conservation of momentum, and we're going to solve a couple of problems using conservation of momentum. First, I'm sort of going to I don't want to say derive conservation of momentum, but we'll sort of motivate conservation of momentum by looking at the impulse experienced by two cars as they bounce off one another, and we'll take a look at that here in a second. Most of the notes in this video here are going to be handwritten because it's just a lot of sort of drawings and equations that I want to sort of work through. So I didn't really type up too much, but I'm going to get into the sort of writing of these things by hand a little more. So maybe the first thing to mention here is that we're going to be able to, in some cases, use conservation of momentum to solve problems, and in other cases we'll be able to use conservation of momentum and conservation of energy. So we need a kind of handy way to abbreviate both, and so I use this COP here to signify conservation of momentum, because we usually write momentum with a P, right? So I use COP for conservation of momentum. I use COE for conservation of energy. Okay, and we'll see that used later. I just thought I'd mention it to start off with here. Okay, so starting off, I guess the first thing to say is that in a closed system, momentum is conserved. Okay, so any system that doesn't have any outside influences, the momentum in that system is going to be the same for all time. Okay, and so we're going to start off by looking at a system of two cars. Okay, so we have two cars, and we're going to take a look at what happens sort of as these two cars, and these two cars are going to be driving in one dimension. So let me maybe draw this. Okay, so before, we're going to have some car 1 with a mass 1 and some velocity v1 driving in this direction. We're also going to have some car number 2 with mass 2 and velocity 2 driving in this direction. Okay, and so this is meant to be a closed system here. So imagine no outside influences, so there's no net force acting on the system. Okay, and so with this closed system, we're going to be taking a look at what happens if these two cars collide. So let's say that originally we have velocity 1 greater than velocity 2, and this is all happening in one dimension, right? So we can imagine that we have like our one-dimensional axis running in this direction. Okay, and so if v1 is greater than v2, eventually car 1 is going to smash into car 2. Something's going to happen during that collision, and then the two cars will continue off doing whatever it is they're going to do, depending on sort of what the initial conditions of this collision tell us is going to happen, right? And so let's take a look. Initially, we're going to have so before the collision, like during what we see in this first diagram here, we're going to have some initial momentum for car 1 and some initial momentum for car 2, and this is going to be our total momentum inside the system. Okay. Now after the collision, we're going to again have car 1 excuse me. We're going to have car 1 moving off now with, maybe I'll write it on top, with v1 prime. So I'm going to use prime from now on to indicate whatever that variable is after the collision. Okay, so we had v1 before, now we have v1 prime, so this is the velocity for car 1 before the collision. This is the velocity for car 1 after the collision. Excuse me. Okay, so we'll also have car number 2 after the collision. And it'll have velocity 2 prime after the collision, right? And so again, closed system. Again, we have no net force acting on our system here. And as we had above, we're now going to have P1 prime after the collision plus P2 prime, and this is going to be equal to our P total, right? And so after the collision, we can say that now our V2 prime is going to be greater than our V1 prime. So sort of what are we saying here? We can see that originally car 1 is creeping up on car 2, and it's going to smash into car 2, right? And after the collision, V2 prime is larger, so after the collision, car 2 is speeding off more quickly than car 1, and they're separating, right? And the other important thing to note here is that P total is the same in both, right? Okay. That is telling us, and this is sort of just a thing that we're asserting here, but this is telling us that momentum is conserved in these closed systems. Okay, so all momentum is conserved in these closed systems. There's nothing happening, there's nothing affecting the system from the outside, so there's only the momentum on the inside of the system, and momentum in the system is conserved. Okay, so let's take a look at what happens during the collision. We're going to take a look at the impulse experienced by car 1 due to the force of car 2 on car 1, and the impulse experienced by car 2 due to the force of car 1 on car 2. Okay, so maybe I'll make a note here. Okay, so as the cars collide, what do we have happening? Well, we have the impulse experienced by car 1, and this is going to be equal to the force experienced or the force applied by car 2 on car 1, and the amount of time that the cars are in contact for, right? And we're going to have the impulse experienced by car 2. This is going to be equal to the force exerted by car 1 on car 2 times the amount of time that the cars are in contact for, right? And so we can kind of see already where this is sort of headed, right? Because whatever the force applied by car 2 on car 1 is, it has to be equal to the negative of the force car 1 applies to car 2, right? This is the same sort of collision happening, and by Newton's third law, we know that every force is going to have an equal and opposite force experienced, right here. So we have car 1 applying a force to car 2 and car 2 applying a force to car 1. These are going to be equal in magnitude but opposite in direction, so we pick up this minus sign. But if that's true, then it must also be true that the impulse experienced by car 2, which is equal to well, we saw that it was equal to the force supplied by car 1 on car 2, well, then it must also be true that it's equal to minus the force applied by car 2 on car 1, right? Times the time that they're in contact for. But then this means that this is also equal to the impulse experienced by car 1, well, the negative of the impulse experienced by car 1. And so what is this really telling us? Well, this is telling us that delta P2 is equal to minus delta P1. And we can rewrite this as delta P1 plus delta P2 is equal to 0. And this right here, this is already our first sort of way to write the conservation of momentum. Okay? So this is the first way we should think about conservation of momentum. Let's then break up delta P1 and delta P2 into its original, its pre-collision momentum and its post-collision momentum. So if I break up delta P1, I end up with P1 final, so like the momentum that car 1 has after the collision, minus the momentum it had before the collision, right? So this is just the definition of delta P1 Do I have space here? I do. Okay. So this is just the definition of delta P1, and then we can have the same for delta P2, and we know this is equal to 0, right? So now I can just shuffle the pre-collision and the post-collision stuff sort of to the other side, or to opposite sides, I should say. This already is another statement of conservation of momentum, but I won't sort of box that one. We don't use it in that form that often. But if I do separate it out, we're going to see we end up with P1 prime plus P2 prime equals P1 plus P2, right? And this is sort of a very useful form that we're going to use most of the time, okay? And this is again conservation of momentum. And we're going to use this form to sort of add up all the momenta before a collision and all the momenta after a collision, and we know these have to be equal, and this helps us solve a number of problems, okay? And so I'll just leave that definition as it is here. There's a few other ways that we could write it down. Another sort of implication of conservation of momentum simply tells us that the total momentum as a vector is equal to a constant in a system, right? So that's a third way to think about conservation of momentum. But we're mostly going to make use of this form of the equation. So let's do that. And we're going to do that by looking at what are called elastic collisions. And this is going to be an elastic collision in one dimension. So we're going to see that there's a few types of collisions. There's going to be elastic collisions, which I'm going to talk about here. There's going to be totally inelastic collisions, and there's going to be stuff that's sort of in between. We're going to take a look at all three of these types, but for now, let's focus on these elastic collisions. And so, well, first we're going to start out by looking at it in one dimension. Okay, so elastic collisions in one dimension is going to be the sort of topic we're looking at here, and also the example that we're going to be doing. So when we think of elastic collisions, we want to be thinking of two hard objects bouncing off of each other, right? So like two billiard balls bouncing off of each other. We don't want to be thinking about two things that kind of stick together and move on, or things that softly bounce off each other and deform. These are like two very hard objects that bounce off of each other, barely deform at all, and move off in their own directions, okay? And so in this specific type of collision, when we have this elastic collision, this collision of two hard objects bouncing off of each other, we don't just have conservation of energy, we also have, or conservation of momentum, I should say, we also have conservation of kinetic energy. So in this special case, where we have an elastic collision, we can use conservation of momentum, and we can also use conservation of kinetic energy. And using both of these tools together is going to let us solve some problems. We're going to see that we can generate two equations, and we're going to have two unknowns, and so we need both of these equations to be able to solve for the variables that we're looking for. And so really the best way to get into this whole conservation of momentum topic is to just do as many examples as we possibly can. So I'm just going to start off with this first example here. It's a little bit of a longer example, so it'll take us to the rest of the video. And I'm going to do it kind of in two ways. It's really just doing it in one way, but reorganizing variables to show that we can kind of solve for one variable first or solve the other. It doesn't matter. We're going to find the same result in both cases. Okay, so what do we have here? We're trying to calculate the velocity of two objects following a collision in one dimension, given the following initial conditions. Okay, so we have some initial conditions. Maybe I'll draw out the problem here. So we have some, it doesn't really matter what these are. We can imagine these are balls or something or whatever. We have some mass m1 with some initial velocity v1, and it is going to hit this mass 2. Maybe I drew these too small. Mass 1, mass 2, and it's going to hit this object m2, right? So m1 is going to smash into m2 because v2 is 0, so this object is really just sitting here, and v1 is non-zero, so they're going to smash into each other, and we're again looking in one dimension here, so only along the x-axis, okay? And so let's take a look at what we have going on here. And so I should mention, the text here doesn't suggest it, but we are looking at this collision as an elastic collision. Okay, so I'll make a note. The title has it, but I didn't put it in the text here. So we do want to remember we're dealing with an elastic collision. So elastic collision implies that we can apply conservation of momentum and we can apply conservation of energy. Okay? And so let's start off by taking a look at conservation of momentum. So conservation of momentum implies that we can write down this equation, right? And at this point, it's probably easiest for us to just substitute in what these values would be. So P again, let's just remind ourselves, P is just mv, right? So our momentum is just equal to our mass times whatever the velocity is at that time. So P1 is basically just m1 v1. P2 is just m2 v2. But we can right away get rid of this term because we see that v2 is 0, right? And so this term goes to 0. And this is going to be equal to m1 v1 prime. And v1 prime, again, let's remind ourselves, is what the velocity of mass 1 is going to be after the collision, right? Plus m2 v2 prime, and again, v2 will be the velocity of object 2 after the collision, right? And so we can clean this up a little bit because we've had that one term cancel out. So we have m1 v1 equals m1 v1 prime plus m2 v2 prime. Okay, and let's just call this equation, we'll call this equation A, and now let's take a look at what conservation of energy gives us. Okay, so conservation of energy implies that the kinetic energy of object 1 initially plus the kinetic energy of object 2 initially is equal to the kinetic energy of object 1 after the collision plus the kinetic energy of object 2 after the collision, right? And this is what conservation of kinetic energy means. It means that we have the same kinetic energy before the impact as we do after, right? And so let's remember that kinetic energy is just a half mv squared. And so we can, just as we did above for momentum, we can rewrite these kinetic energy terms. What do we have? We have 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And again, this term goes to 0 because v2 is 0. And this is equal to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared, right? And again, as we did above, we can clean this up a little bit. I'm going to multiply both sides by 2 to get rid of those factors of a half. And if we do that, we can simply write m1 v1 squared is equal to m1 v1 prime squared. Oops, that looks like a 3. Plus m2 v2 prime squared, right? And let's call this equation B. Okay, so what do we sort of have here? Well, we have well, maybe first, what do we know? We know what M1 and M2 are, and we know what V1 and V2 are, right? So if we know what M1 and M2 are, all these M's are known. V1 and V2 we know, so all these V's without primes we know. The only things we don't know are V1 prime and V2 prime, right? So we have 2 equations and 2 unknowns, so in principle this should be a solvable system. Let me get us another page here. So 2 equations, 2 unknowns. This tells us that this is a solvable system, okay? And so let's take a look at how we would solve this. This is, from this point forward, it's really just a matter of algebraic manipulation and then the solving of these two equations. So let's take a look at A, our equation A. We can clean it up a little bit. Let's in this case we're going to isolate the v2 prime. Okay, so we want to isolate one of the unknown variables in this case. So we're going to isolate v2 prime, right? So I'm going to rewrite this. So I can factor out. Well, maybe I'll just fully. Can't quite get both of them on the page here. So let me write it like this: m1 v1 equals, and what did it equal? m1 v1 prime, m2 v2 prime. m1 v1 prime plus m2 v2 prime. Okay, so let's shuffle over the m1 v1 prime from the right to the left here, and let's factor out an m1. So we're going to end up with m2 v2 prime equals m1 v1 minus v1 prime. Okay, and then it's really simple for us to simply divide through by m2, and we can get a new equation: v2 prime equals m1 over m2 v1 minus v1 prime, right? Let's call this equation C, and now substitute equation C into what we called equation B up here. So let me maybe rewrite equation B. Equation B was what again? It was m1 v1 squared is equal to m1 v1 prime squared plus m2 v2 prime squared. Right, but now we have this expression for v2 here in our equation C, or v2 prime I should say. So let's substitute in this equation for v2 prime and see what we get. So we end up with m1 v1 squared equals m1 v1 prime squared plus m2, and this would normally be v2 prime squared, but we now have this expression, so we have this m1 over m2 v1 minus v1 prime all squared. Okay, so I have some numbers here for later on, but let me pull out that page. Okay, well we'll keep manipulating this algebraically, and then I'll substitute in numbers afterwards. So we can see that we can sort of handle this square that we have up here. We want to kind of expand that out, so let's do that. If we do that, we end up seeing that we have m1 v1 prime squared plus, and hold on for 1 second, why do I have m2 m1 squared? Oh, I might have an error in my notes here, 1 second. Excuse me. M2, M1. Okay, well, my numbers in the end may, well, I'll double check it here. Okay, so let's expand out what's happening inside those brackets. So we have an m2 here. If we do the squaring here, we can square the first term. We're going to end up with an m1 squared over m2 squared, and we're going to have a v1 minus v1 prime squared, right? So we can continue to simplify m1 v1 prime squared plus, and we're going to have this cancellation here of one of the m2's. So we're going to have m1 squared over m2, and then we have to FOIL out these brackets. So we're going to end up with a v1 squared plus v1 prime squared minus 2 v1 prime, right? That looks good. So now let's shift everything over to the right hand side, right? We still have this term on the left hand side. So let's shift that over. This is going to give us an equation that looks like this. We have 0 equals m1 v1 prime squared, and then the term that we shifted over, m1 v1 squared. And I'm going to expand out that bracket there, so we're going to have m1 squared over m2. Oops, that should not be squared. There we go. Times v1 squared plus m1 squared over m2 v1 prime squared minus m1 squared over m2, and maybe I should put the 2 out front, v1 prime. Okay, so this is just me shifting the term from the left-hand side over to the right, and then expanding out these brackets. But maybe we can start seeing what's happening here. Let's start grouping these terms up in a sort of suggestive way here. Let's see. So we have this term that goes like v1 prime squared. We also have this term that goes like v1 prime squared. So maybe we want to sort of group those terms together. We also have a term that goes like v1 prime to the power of 1, right? So let's group those up, and then we'll group up the terms that don't have a v1 prime in them at all. If we do that, we end up with an equation that looks like this. So v1 prime squared. What did we have multiplying v1 prime squared? We had, well, over here we had m1, so m1. And then over on the right there we had m1 squared over m2, right? So that's great. What do we have hitting our v1 prime to the power of 1 here? Well, all we had was that one term, so it's a minus 2 m1 squared over m2, right? And then we had some leftover terms. We can clean those up a little bit. I'll just put that all in a bracket, and it's going to end up as a v1 squared, put this in a square bracket, times m1 squared over m2 minus m1. Okay? And so now written in this form, we can maybe see what's kind of happening. What do we have here? Well, what we have is a quadratic. Excuse me. Quadratic in v1 prime, right? We have a v1 prime squared term, a v1 prime to the 1 term, and a term that doesn't go like v1 prime. So we can solve this using sort of our methods to solve quadratic equations, right? And at this point, if we were doing this with a calculator, which I kind of did this one, right, we would substitute in numbers. We know that m1 is 0.5. We know that m2 is 3.5. What else do we know? I don't remember what v1 was. v1 was 4. Right? And that's basically all that we need, right? We already canceled out all the v2s that were 0. And so if we just substitute in these numbers, we're going to end up finding that we have an equation. So like substituting in for m1 here and m1 and m2 here and so forth, we're going to end up finding that we have an equation that looks like this. This will be 4 over 7 if we clean it up. This will be minus 4 over 7. And we're going to end up having a term that goes like, after simplification, it's going to be minus 48 over 7. Okay? And so we can identify that this is our A, this is our B, this is our C, and we can solve for v1 prime, which is just going to be minus b plus or minus a square root of b squared minus 4ac all over 2a. And if you substitute in these numbers and you go through the whole solution, you're going to find a solution for v1 prime that is equal to 4 or minus 3. Okay? And at this point, we kind of have to use our physical intuition to decide which of these is the better solution for what v1 prime is going to be. So we have to kind of have to look at the problem and think about it, right? So what do we have going on here? We had a v1 of 4, and then m1 smashes into m2. M1 is much lighter than M2, and this is all happening in one dimension. So what's going to happen here? Well, clearly the answer can't be 4, right? Because this thing smashes into a heavier object. What do we expect to happen if it's a hard object that's going to bounce off of each other? Well, we expect this M1, so we expect that M1 is going to bounce off of M2 and bounce back in this direction, right? And that's what this result of minus 3 gives us, right? So this result of 4 is really what would happen if these two objects missed each other. If this object was coming like this and somehow it just zipped by, it would still have a velocity of 4 meters per second. But they do collide, and so we choose the minus 3 to reflect that. So we choose a v1 prime equal to minus 3 meters per second. Okay, and that's great. Now that we have v1 at minus 3 meters per second, we can very easily go back to equation C here. I'll recopy it here. It's v2 prime. v2 prime equals, is it m1 over m2? It is, and it's v1 minus v1 prime. So v1 minus v1 prime. We know what all of these are. M1, M2, and v1. We just solved for v2, and if we substitute it, well, I guess I can just do it. We end up finding that's 1/7 times 7 equals 1. So we end up finding a v2 prime equal to 1 meter per second. And so let's just think about again what happens. Let's look at our diagram here. We had the heavier object stationary, so we had this M2 was stationary. It's 3.5 kilograms. It's just sitting there. This lighter object comes up on it at 4 meters per second, smashes into it. The lighter object bounces backward in that direction with a velocity of 3 meters per second in that negative direction. And M2, the heavier object, now starts moving off in this direction at 1 meter per second. That seems to sort of fit what our physical intuition of the problem would be. All the numbers seem to work out, and so that's great. The sanity check is sort of passed, and we can move on. So I just wanted to do a very quick additional sort of look at the solution here. Could we have done this slightly differently, right? We had, let me recopy equations A and B here. I think I remember them. So we're going to end up having, well, we had M1 V1 was equal to M1 V1 prime plus M2 V2 prime. That was our equation A. And we also had M1 V1 squared was equal to M1 V1 prime squared plus M2 V2 prime squared. That was our equation B. Could we have solved this differently? Last time, what did we do? We chose to isolate V2 prime, right? So, I mean, we can probably already tell that this is going to work out, but let's do it anyway, just to be sure. We could instead of isolating V2 prime in A, we could use A and isolate V1 prime. If we did that, we would find that V1 prime is equal to V1 minus M2 over M1 V2 prime, right? And now we can just substitute this back into our equation B, right? So we have a V1 prime here, and we can just substitute it back in there. So let's do that. So we'll call this C. So C in B gives us what? Well, we end up with M1 V1 squared equals M1, and now this is the squaring of our new term. So we have V1 minus m2 over m1 v2 prime squared plus plus m2 v2 prime squared, right? And so to clean this up, I'm just going to divide through by an m1, and I'm kind of doing this more quickly because this is basically the same as what we just did above. I just want to see that it's going to work both ways. We know it has to, but just for fun, let's do it. So I'm going to divide through by an m1, and this is going to give us an m1 here, right? Okay, so let's expand this out a little bit and clean some stuff up. So we're going to end up with our v1 squared equals. I'm going to end up with v1 squared in here as I expand out this this bracket. I'm going to have an m2 squared over m1 squared times v2 prime squared. I'm going to have a minus 2. This is from the sort of cross term. We're going to have a minus 2 m2 over m1 v2 prime v1, and then we have this leftover last term left here, right? So we can subtract this term from both sides, and then we can kind of start to group things up, right? We can see that we have two terms that go like v2 prime squared, this term and this term. We have 0 left on the left hand side, so I can kind of clean this up and group it up like this. We'll have a v2 prime squared. This is going to be times our m2 squared over m1 squared plus our m2 over m1, and we're going to have this leftover term that goes like v2 prime, which will have a coefficient of maybe I should make that a plus, and I'll do it like this, minus 2 m2 over m1 v1, right? Again, quadratic, right? Quadratic in maybe I'll write it, quadratic in v2 prime. And so if we solve, like we know what m1 and m2 are, if we shove in all the numbers for that, we're going to find this is going to be our a. This is going to be equal to 56. And our b here, if we put in all the numbers, we're going to find a b of minus 56. Okay, and our c clearly will be 0, right? There's no term there. So if we then use the quadratic equation, is then going to lead us to a value of v2 prime equal to 0 or 1. Okay, and so what is 0? Well, 0 corresponds to what would happen if the collision never happened, if these two objects missed and slid past each other, right? Our v2 prime, just as we saw above here, our v1 prime would have stayed 4, and now we're seeing that our v2 prime would be 0 if the collision didn't happen. So v1 would be equal to v1 prime, v2 would be equal to v2 prime if these two objects just flew past each other. But if the collision happens, we saw up here that we're expecting a v2 prime of 1 meter per second, and we just confirmed it down here. So we do in fact find a v2 prime equal to 1 meter per second after the collision, right? And then obviously we can just resubstitute. I won't bother doing that here, but we can obviously just resubstitute this v2 prime back into our equation C, and we're going to find that we have a v1 prime equal to minus 3 meters per second, as we found above also. Okay, so that's our sort of first look at conservation of momentum and elastic collisions in one dimension. We're going to look at other types of collisions in later videos, and we're going to also expand this to more than one dimension. But for now, we'll leave it there.